Okay, thanks a lot for the invitation. So I'm the second person with a French accent in this session. So bear with us, please. Okay, so today's talk is about machine learning for indoor acoustics. So I first want you to imagine that you are in a pitch dark room, complete darkness. Okay, then you clap your hands and you listen. Can you guess what is the shape of the room? And even harder, can you guess if the floor is made of tiles or carpets? Okay, so to address this type of problem, first I will need to introduce a little bit of background in audio signal processing and in acoustics. So I will try to be short here. And then I will introduce a quite general framework, which I will call virtually supervised learning, which is one way of tackling this type of problems. And then hopefully I will have time to show you some examples and some results, like 2 or 3 maybe. And I will conclude the presentation. So it's going to be rather short. Okay, so let's start. So first things first, what is sound? So sound is a mechanical vibration. You can see it as like some dominoes falling, right? So some molecules are moving in the air and this is propagated. This results in a variation of air pressure, some very small local variations of air pressure. And this can all be modeled using the well-known wave equation. It's a 3D wave, right? Okay, so sound has a speed, 343 meters per second. Sound dissipates, roughly minus 6 dB every doubling of the distance. And sound, most importantly for us, interacts. So we can distinguish mostly three ways sound can interact. So sound can be absorbed by surfaces and materials in the room, or it can be transmitted. So this is what happens when you hear your neighbor in the flat next to you, for example. Sound can be reflected, very importantly, and it can be reflected mostly in 2 ways. It can be reflected in a specular way, which is a bit like on a pool table, you know, or when you look at yourself in a mirror. So these are like the famous Descartes laws. Or it can be reflected in a diffuse way, which is more like random. Okay. So now if we go back to our initial problem, when I clap my hands in the room, the sound bounces all around the room. It's either absorbed, transmitted, diffused, and then it goes back to my ear. And this is a phenomenon that we commonly call reverberation, you know, and it's this annoying thing when you are in a classroom which has bad acoustics and you have this reverberation phenomenon that you can hear very well. Okay, but now if we are not talking about my ears, but about a microphone, how can I model reverberation in a microphone signal? Okay, so moving on, we are going to talk about room impulse responses. Okay, so impulse responses are essentially the response of a linear time invariant system to a perfect impulse, or a Dirac. And a room impulse response in particular captures the linear filtering effect due to the propagation of sound from a point source to a microphone inside a room. So it looks like this. You have as an input a perfect Dirac, a perfect impulse in time domain. And at the output, you have something which looks like this. So here on the y-axis, we have the pressure and we have time, and we can even listen to it, hopefully. Okay, so it just sounds like a big bang. Okay. And while this is made of different parts, and we can usually notice at first we have the direct path, which doesn't arrive immediately because sound takes time from going from the sound source to the microphone. And then we have some early reflections, which we can also call the echoes. And then you have some diffuse late reverberation. And also to note is that the room impulse response can be transformed in the Fourier domain. And then we talk about the room transfer function. And then you can capture with it the effect of the room in different frequency bands, right? Okay, so why is this useful, this concept of room impulse response? Well, because it can be used to reverberate any dry sound signal. So if you give me any sound signal with no reverberation, for example, speech recorded in an anechoic chamber, using a simple convolution, then, sorry, like I have some technical issues. Yeah, so using convolution, I can essentially make this signal reverberant. So it's convolution in the time domain, but in the Fourier domain, it's even simpler. It's just a multiplication with a transfer function. So let's just listen to an example. So here we have some dry female singer. I multiply this in the frequency domain with a transfer function of a church, which is on the picture here. It sounds like this, and the result is this. All right, so using room impulse responses, you can convincingly generate, reverberant audio recordings. And of course, this can be generalized to multiple microphones, to any kind of microphone antenna, linear, circular, spherical. Okay, so now if I summarize everything, if I'm given some source and receiver positions in a room and together with their acoustic properties, if I'm given the room geometry, if I'm given the acoustic properties of all the surfaces in the room, I can transform that into some room impulse responses. And in turn, I can obtain some reverberated audio signals. So the first arrow here is quite easy. You can do that with the room acoustic simulators. I will talk a bit about that later. And the second arrow is also easy. You can just use, as we saw, convolution. However, today we are interested in the opposite direction arrows. So how can I go from a bunch of measured room impulse responses to the acoustic properties of the room? And even harder, how can I go directly from reverberated unknown audio signals back to the room geometry or the properties of the room surfaces? All right, so those are really difficult, but really interesting inverse problems, okay? But why do we care, you may ask? So I will try to explain you three main application domains for these questions. The first one is indoor noise disturbance. So we've all experienced when you're, as I said before, in a classroom or a restaurant, which is very loud. This is not nice, so you would like to find a solution to improve its acoustics. And what we could do with these techniques is to make acoustic diagnosis faster and better, maybe. Another application domain is audio augmented reality. So let's say you have a user wearing a augmented reality headset, and you have some true sound sources in the user's environment, but you would like to add virtual sound sources. But to do it in a convincing way, you will need to somehow access the acoustic characteristics of the user's environments. And a third application domain, which is actually very close to the application domain that Mark talked about just before me, is what we call echo-aware audio signal processing with applications to hearing aids or vocal assistant devices. And the idea here is to try to make use of some known properties of the sound propagation in the environment to improve signal enhancement or audio signal processing techniques. Okay, moving on to the key topic of the talk, which is virtually supervised learning. So if I'm given some audio inputs, I can compute some features from them and extract some kind of feature vector. And then the question we have is, how can I go from this feature vector to the acoustic or geometrical properties of the room or of the sound scene? All right. So the first approach we can use is a physics-driven approach. Okay. So to do that, we need a forward physical model of sound. So it could be a simple model or a complicated model. And if you're lucky, you will have even like a closed form formula, which allows you to reverse this physical model and go directly using a formula from the vector to your geometrical properties. So this exists in practice. So for example, when you want to compute the direction of arrival of a sound source, you have a closed form formula which connects this direction of arrival with the time difference of arrival at the microphones. Another example is the Sabin formula, which connects the reverberation time of the room, the volume of the room, the surface of the room, and the absorption coefficients of the room, right? So if you have three of these four quantities, you can directly estimate another one using this formula. Okay, so this is very good because you don't need any kind of training data set. It's not learning based. It's also very computationally efficient, obviously. It's a simple formula, but obviously it's going to suffer in complex conditions. All right, these are very limited formulas, and they are limited also because you cannot do everything with it, right? If you're in a very complex scenario, of course, it's not going to work. Okay, if you are less lucky, you are not going to have any closed form solution, but what you can do is you can use optimization-based inversion. So you're going to try essentially to minimize the norm between your observation vector Y and operator A, the forward operator, applied to your acoustic parameters, okay? And there are some interesting works doing that, but we are not going to talk in depth about it today. So the good thing about these approaches is, again, they are not learning-based, so you don't need any training data. However, they are usually non-convex techniques that are hard to inverse. And also they are going to be sensitive to model mismatch. So here, the choice of model A is very important. If the reality doesn't match your model, it's not gonna work very well. Okay, so we can move on to a second type of approaches, which we could call the real data-driven approaches. Okay, so here we suppose we have access to some training audio inputs from which I can extract features. And on top of that, I have some annotations for these audio inputs using some sensors or some data sheets or whatever. And because of that, I have a training data set which directly maps some feature vectors to the acoustic geometrical parameters that I'm interested in. Okay, so now you can use your favorite machine learning technique. You get a learned model, and then this learned model can be used in a regression or classification fashion to map a new feature vector to some acoustic geometric parameter. Okay, so here I show you a quick video. So this is me during my PhD thesis, and I'm holding a loudspeaker in front of a camera, and the loudspeaker is emitting white noise. And then at every point where the loudspeaker is emitting white noise, I'm recording the sound and I'm checking the position in pixels inside the camera frame, right? So exactly as I explained, I have a data set of audio sounds and I have the corresponding geometrical annotation, and all is good. I can use machine learning to do sound source localization. Okay, so this is actually very accurate. Like you can go down to very, very good precision. It's quite robust to noise because you can easily add noise to your training data set. But obviously, it's quite specific to the room on which you trained your system, so it's not very practical. And of course, the most obvious one is that it's extremely costly to acquire. Like you can spend like hours or days, and this is not very reasonable and scalable for real life applications, right? Okay, so now we arrive at virtually supervised learning, which is an attempt to take the best of both the physical world and the data-driven world, right? So in that case, we are going to use a forward physical model, and we're going to use this model to generate some training simulated signals. And for free, we are going to get the annotations because we generated these signals. Then you get a training data set, and you can again use machine learning on it to get a learned model. All right, so the good thing here is that you have virtually unlimited data for free, thanks to your simulator. It's quite robust. Because you can like add any kind of noise or change any kind of parameter in your model. And it's also physics based. But the big question is it going to generalize to real data, right? So we train in the simulated world, but is it going to generalize? And this is the key point I want to address with you today. Let me check the time. Okay. So you are going to have to face some trade-offs. And essentially, there are two big trade-offs you have to face. The first one is a trade-off between realism and computational complexity. And the second one is between diversity of your training set and the size of your training set and the resulting size of the model you are training. Okay, so let's start with the first one. So you have different room acoustic simulators out there. So the first category are discretized wave equation solvers, such as FDTD methods. But the good thing about them is that they can solve, like in theory at least, they can solve any type of wave equation conditions, but they become quite intractable above, let's say 4 kilohertz, because you need to discretize the space with a very fine grid. Then you have the image source method, which is essentially like you break all the walls of your room, you remove the walls and you replace them by virtual sources, which are simulating the reflection of the sound on the walls. So this is very fast, but it doesn't capture very well the low frequency effects, and it only works for specular reflections. And then you have energy-based, ray-based, or particle-based methods, which are essentially sending sound energy from the source in the form of rays or particles, bouncing them around in the room, and then there is a receiver which receives all of these rays at the end of the process. So this is very versatile, but it doesn't capture low frequency effects very well either. And it only captures approximately the time of arrivals of sound. So I can advise for this type of trade-off, there are two simulators out there. So you have RoomSim by Schimmel and colleagues, and you have Pyroom Acoustics, which are basically combinations of the image source method with some ray-based method in a quite computational efficient way. So we found that these are actually pretty good trade-offs if you want to train your neural network model. Okay, and what about diversity versus training size? So you are going to have to make some decisions. What is the room size? Are we talking like about a toilet or an office or an airport hall? So you need to define a bit of a range in terms of room size. what's the room shape? So it could be a shoebox room, which is very common, or it could be an auditorium, or it could be an underground cave, I don't know. What's the room acoustics? Are we talking about the Abbey Road studio, a cathedral, and so on? And also, what about the source and the receivers? So you can have like omnidirectional sources and receivers, but you could have like sources which are not omnidirectionals, like human speakers. You could have receivers like hearing aids, and so on. So a good compromise that we found and that we will use in the experiments is to use random shoebox rooms with lengths and widths randomly picked between 2 meters and 10 meters, and heights randomly picked between 2 meters and 6 meters. And then we basically use omnidirectional sources and receivers everywhere, and we place them randomly in the room with like a safety distance of 1 meter between everything. And then you can build easy like this a data set of 10,000 to 100,000 room impulse responses using those simulators. Okay, but I didn't talk about the acoustic properties of the surfaces in the simulator. You know, how do you choose your surfaces? So a good trade-off we found is to use diffusion coefficients for the surfaces, which are basically the same for all surfaces, but which are a bit lower in low frequencies and higher in high frequencies. And this is meant to emulate like typical surfaces that you can have in a room, but also to somehow model what could happen inside the room. For example, if you have people in the room or furniture in the room, it's going to add some kind of randomness in the reflectivity. And you can simulate that by having like a constant diffusion coefficient inside your entire room. Then what about the absorption coefficients? So each of the walls is going to absorb part of the sound energy in different octave bands. So typically we use like 6 octave bands from 125 Hertz to 4000 Hertz in a logarithmic scale. And we discovered a quite nice way to simulate in a realistic way absorption coefficients. So we developed what we call the reflectivity biased acoustic sampling strategy. And the idea is that for each surface type, wall, ceiling, floor, you toss a coin. If it's on head, you are essentially going to draw a flat material, like something with a absorption coefficient which is very low, between 0 and 0.12, and which is flat in frequency. So that simulates like reflective surface, like concrete, for example. And if it's on tails, you are going to randomly draw a profile inside a realistic range depending on the surface type. Okay, and here I just show you 2 histograms. So the blue one is what happened to the reverberation time of your room when you completely randomly pick the absorption coefficients between 0 and 1, which is the naive thing to do. And as you can see, it generates like quite unrealistic rooms. So the reverberation time is very low in that case. On the other hand, if you use this strategy, the reverberation time will be much more widely spread, and you will have much more realistic rooms. Okay, so moving on to some examples and results. So the first example I want to give you is how to go from some room impulse responses to the mean absorption profiles of the surfaces in the room. Okay, so this is the question. Okay, what was the question? Is there a carpet or tiles on the floor of my room? Okay, so we can define the mean absorption profile of a room as the weighted sum of all the absorption profiles as a function of the octave band, weighted by the surfaces in square meters of every room. And to do that, we are going to compare 2 very simple deep neural networks, so a multi-layer perceptron, I skip you the details here, and a convolutional neural network. Okay. So we now are going to test the trained neural network using the strategy I just explained to you. And we're going to test them on simulated rooms first. So 5 different geometries, 500 reals. And we're going to compare the 2 training sets, the uniform absorption coefficient or reflectivity biased. And we're going to compare the 2 neural networks against the classical laws from Acoustics, Sabin, and Ehring, which I mentioned earlier. Okay, so these are the results. On the y-axis, we have the absolute error on the mean absorption coefficients. And what you can see here is that using the uniformly sampled training data set, we get very bad results actually. Using either perceptron or CNN, it doesn't really work. We get worse results than using the classical formulas from Acoustics. So this is really bad news. However, if we use this trick of sampling the acoustic properties of the room correctly, we can actually pretty significantly outperform the classical formulas, whether we use a MLP or a CNN. And we also tried, of course, to see if it generalizes to real data. So we have a data set that we recorded in a modular acoustic room with 900 room impulse responses in 10 different room configurations. And we divided our room impulse responses in the nice room impulse responses for which the reverberation decay was easy to estimate, and the unusual room impulse responses. And so if we only look at room impulse responses in the nice subset, we can see that for all the rooms, we get results which are comparable to the classical acoustic formula. So there is some sort of generalizability of the simulated training, the virtually supervised learning to real data. So if we look at each of the room, we see that we have comparable performance between CNN and the Herring formula. And now if we look at a comparison in terms of the learning-based methods between the easy room impulse responses and the hard room impulse responses, we see that actually the neural network doesn't care if it's a nice or hard room impulse responses. It generalizes very well, whereas the classical method like the Herring formula, it really relies on the reverberation time, and to estimate the reverberation time, you really need a nice room impulse response. Whereas the neural network doesn't care, it actually generalizes better. Okay, so that was first example. I have a second example, which I will maybe skip here because I don't have much time, which is about estimating the time of arrival of the first reflections in a signal. So once again, you can use virtually supervised learning, and we have some results with that. And finally, the last one is blind room parameter estimation. It's a recent paper we published 2 months ago at WASPA. And we try to jointly estimate the volume, the total surface of the room, the reverberation time of the room in octave bands, and the absorption coefficients. So we developed a specific neural network architecture. I'm not going to give you the details, but one of the key properties, it's an architecture that enables you to aggregate multiple observations inside of the same room using some Bayesian technique. Okay, so here are some results. So in blue, you see the results using 2 channels, so 2 microphones, and in red using a single microphone. And on the x-axis, you have the number of positions inside the room that you use, so from 1 to 5. And as you can see, is that for every quantity we try to estimate, it actually helps to use more positions inside the room to aggregate multiple observations. And it seems that for surface and volume estimation, having 2 ears is actually helpful. For reverberation time and absorption is not so helpful. So if you want to know if you have a carpet, a single ear is sufficient. But if you want to know the volume of your room, apparently having 2 ears is better. Okay, so it's time already to wrap up. So recovering the geometry and acoustic profiles of a room from a clap is very far from solved, of course. I didn't mention it, but below 1000 Hertz, actually at low frequency, it's actually very challenging. We don't get good results yet, mostly because of the simulators that we are using. A next challenge would be, of course, to estimate the individual properties of objects in the room. So far, we were only interested in like global properties, but individual properties would be really interesting. There are a variety of open and useful inverse problems in acoustics that you can be interested in. And of course, like the ultimate question, the $1 million question is like, how can you combine acoustics, machine learning, and signal processing all together in an optimal way to develop such methods? And I'm very obviously interested in that. And some promising directions are domain adaptation, transfer learning, using generative models, adversarial networks, and trying to develop some sort of neural rear generation techniques. And coming soon, probably in the next few months, my PhD student and I are going to try to release an extension of Pyroom Acoustics that enables to load measured source and receiver directivity inside the simulator. So directivity is quite often neglected in the literature, and we are really interested to see the impacts of directivity in this type of approach. Thank you very much. And if you have questions, I can answer them by email. My email address is below or after the next talk. Thanks.